Hello and welcome to T1 Day 20 of Honors Precalculus. We're going to talk about Ferris wheels today, those big round rides where you get in a basket and you go way high up. And in this case, we're talking about the largest Ferris wheel, which was unveiled in 2014 in Vegas. And it's 550 feet in diameter, so it goes all the way up here to 550 feet. It's pretty high. It goes really slowly so that people can go on and off without the wheel stopping. We're going to sketch a graph to model the height, h of t, of a person on the wheel as a function of time, assuming that at t equals 0, the person is getting on the wheel. So down here is where time equals 0. And we're going to put on a coordinate system so that we can see what we're looking at. So we know that the wheel turns at a rate of 1 revolution every 30 minutes. We see that right here, 1 revolution every 30 minutes. It takes 30 minutes to go all the way around. And if you hear weird noises in the background, it is my golden retriever trying to contribute to this video. From this information, we're going to complete a table. The key is that it's going counterclockwise, which is in this direction, counterclockwise. So if it takes 30 minutes to go all the way around and it starts at a height of 0, we know that it's going to be back at a height of 0 after 30 minutes. Well, halfway, and we're assuming it's going in even speed. It's going even speed all the way around. It's not speeding up or slowing down. So halfway, it will be all the way at the top. So that's time equals 15 up here. So it's going to be at its highest height of 550. So what does that mean? It means at 60, it's going to be back at 0, and then halfway again, it's going to be at 550. Well, at 7.5 minutes, it's going to be right there. Time equals 7.5 minutes, so it's going to be halfway up. Well, halfway between 0 and 550 is 275. And then it's going to be here at time equals 22.5 minutes. So it's going to be coming back down again. It's going to be coming back down again, but you'll be back at the halfway, the midline, which we'll be talking about, be 275. So all of these are back at the midline here. So they are 275 and 275. So when we fill this in, we end up with this. This is the height off the ground, of the Ferris wheel, of the person on the Ferris wheel every time interval. Okay, what we're going to do now is plot those points on a graph. Well, at time equals 0, it's right here down at height equals 0. So then we plug in 275, which is here, and then at 15, it's at 550. And then the rest of the points will look like these points. Now, we're not going to connect them yet. We're not going to connect them yet because our temptation might be to connect them with straight lines. We're not going to connect them with straight lines. What we're going to do is we're going to fill in this table more granularly at more frequent time intervals. We already know some of these. We know that at 15 minutes here, the height is going to be 550. And at 30 minutes, or is it 30 minutes, it's going to be back at 0. So the ones we know are here. So we know there it's going to be back. It starts at 0. So what else do we know? Every 15 minutes, we have a sampling. So at 45 minutes, we're going to be back at 550. So these are points we've already figured out. So then we need to fill in more of them. We also know these points from the. So those are from the last chart, but we're going to now figure out what about at time equals 2.5 minutes. So we do that by looking at these spokes here. So what I mean by that is we know that it goes from 0 to 7.5, like this right here is time equals 7.5. This right here, 1/3 of that is time equals 1/3 of it, which is 2.5, and this right here is time equals 5. This right here is therefore going to be time is equal to 10. So we're breaking it apart into, you can think of it as the hour divisions of a clock. This would be 6 o'clock, this would be 5 o'clock, up top would be noon. So they're leading you through this by asking how many minutes does it take for a person to move from 6 o'clock to 5 o'clock position. So that would be effectively this distance right there. So what we need to do is if we're going to fill this in, we're trying to find the height right there, the height at 2.5. So we can estimate it right there. The height we're looking for is this distance right here that I've zoomed into green. So we just estimate it to be, I don't know, it's less than 50. It's an estimate. So let's just say it's 46. Let's just say it's 46. So it's a little bit less than 50. So 46, 45 if you wanted to. And then we want to know this height right here. How high is this one right here at time equals 5? It's a little less than a little less than 150. So let's just say, I don't know, 147. 145 would be fine. So what we can then do is then all of these are going to be reflected here. So if you know that this distance right here is the distance, that's the midline, we know the height right there is 275, and we said the height right here was 147. We can do 275 minus 147 and get 128. So that's this distance right there is 128. So this distance has to be 128. So therefore, at time equals 10, that's going to be 275 plus 128 because of the symmetry, which we're going to call it 403. So basically, our choices for these heights right here dictate, these heights dictate all of the rest. So that's 403 at 10. So if you use these, you then get this height right here. We can estimate that one as well, but that's going to be a reflection of this one down here. So what is this distance right here? The purple distance, that's from the midline, so that's 275 minus 46. 275 minus 46 is 229. So that right there is 229. So this height right here is going to be 275, which is the midline height right there, plus 229, which is 504. So at 12.5, it's going to be 504. Everything else is just going to be a reflection here. It's just going to be a reflection. So then it starts going back down. It's 504, and then it's 403 again. And then after that, it's going to be 147, and then it's going to be 46 again. And then it's just going to do the same thing. So you fill this in, and you get the same rows because it's going to repeat every 30 minutes. You should expect to see the same rows here because the same thing's going to happen every 30 minutes. Now, what we're going to do is we're going to connect the dots. Let's put the dots on it and connect them. So I just put on the first few points there, and when I connect them here, you're going to end up with this type of curve right here. And then you know it's going to look, I'm going to try to make that a little smoother, sorry. Goes up through there. I missed it again. See, it's really hard to do this. So I'm going to go up like this, then it's going to go up like this. So that blue point's actually a little bit over right there. And we know this is just going to get repeated over and over again. As you saw in the table, you have the same symmetry. So you end up with a graph. It curves down, curves up, curves. So you end up with this kind of graph. They're not straight. When you plot all the points, you get the first curve. And this curve right here is just going to get replicated over and over again. And because it repeats itself over and over again, it's called a periodic function. The period of a function is the length of time it takes to make one complete rotation. So one time around. The midline is halfway between the bottom and the top, the min and max. In our Ferris wheel example above, the minimum was 0 and the maximum was 550, so the midline at before was 275 feet, so y equals 275. And then the amplitude is the distance from the midline to either the min or the max. It's the same distance. So in this case, the amplitude was 275 because it was 275 to 550. Now, a lot of these numbers in this example are nice because the minimum is at 0. It doesn't necessarily have to be at 0. So just to give you a picture of what's going on here, when we go back up to our graph here, the midline is right here. This is our midline right here. Y equals 275, or h equals h of t, so that the value is 275. And then the amplitude is this distance right there. That's the amplitude right there. And then the period is this distance right here. The period was 30 because it does one complete, it goes up, and then it comes down again and then repeats itself every 30. So that right there, this distance right there is the period. So suppose the wheel was 600 feet tall, what would change? Think about that, it would stretch. So you'd have a max change, and you'd have the amplitude would change because the distance between the midline would be different because the midline would be 300 and the amplitude would be 300 and the max would be 600. So what would change if it takes 10 minutes for one revolution? Well, that would be the period would change. So instead of the period being 30 minutes, it would be 10 minutes. So once you understand these terms, you can make these graphs a little bit faster. Suppose you had a 200-foot Ferris wheel and it takes 12 minutes to make a full rotation. So this is the period right here, and then this would be the max. So if we put 200 all the way up here, and let's say it's 3 minutes, then 6, then 9, then 12, you know it's going to reach the maximum at 6, halfway between, and we know it's going to reach the midline halfway, here, 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 and we know that it's going to curve. We know it's going to curve, so the midline is at 100, halfway between. So when we do this nice curve, it curves up, curves like this, curves like this, curves like this. You could use the copy-paste feature, and you will get better at drawing these curves. I'm doing okay here. That's what it would look like. So the period is 12 minutes. The midline is h equals 100, the height, and the amplitude is the distance from the midline. There's the amplitude right there. That again is 100. Again, our two examples have the midline and amplitude being the same, but that doesn't necessarily mean they're always going to be the same. So in this question, something changes. The Ferris wheel is 35 meters in diameter, but it's boarded from a platform that is 5 meters above the ground. So the person starts at 5. So what that means is we're starting at 5. That's where the person's going to be at time equals 0. And the highest point they're going to be is 35 above that, which is 40. The midline is going to be halfway between that, so that's 40 plus 5 over 2, so that's 22.5. So you get 5, 10, 15, 20 right there, and then 25. So the midline is actually going to be right in the middle here, a height of 22.5. So then it says it spins, the 6 o'clock position of the Ferris wheel is level to the boarding platform, so it's starting here. 6 o'clock is all the way down. And the wheel completes a revolution every 8 minutes. So what we can do is make this 2 minutes, 4, 6, 8. So you're back to here at 8, 10, 12, 14, 16. You're back to here at 16 minutes. So it's going to be up here. It's going to reach the midline halfway. And then you can just fill in all of these other ones really nicely. Now when you graph this, it's actually just going to be this nice curve that goes up. Oh, I like the highlighter better. Makes the curves a lot nicer. It goes up, goes down, goes up. So this is the height of the person. So in this case, the period is 8, and the midline is at 22.5. The amplitude is the distance from the midline to the max height, or the min. It would be the same. So it's going to be 40 minus 22.5. 40 minus, a bad 5. I'll clean that up. 40 minus 22.5, which is 17.5 right there. So last thing it says is then state the period, midline, and amplitude, and all the time you would be at 40 meters. So where would you be at 40 meters? You would be 40 meters at 4, and then also at 12 minutes. So 4 minutes in, you'd be up there, and at 12 minutes in. And then the next one, if you wanted it, would be 8 minutes later at 20 minutes. So if you need a further picture of what this looks like, you have a Ferris wheel, and then it's on a platform that is 5 meters high. And then this was a diameter of 35. And you're getting on right here, and you're going around. I would highly recommend, if you want more practice, to try this one, which is in your handouts right here. Suppose a weight is suspended by a ceiling in a spring. See if you can fill this one in for extra practice.